Good morning to all. Today, as part of SCHEMCON Conference 2022 organized by Department of Chemical Engineering and ISHE HRC, we are having our first invited talk by Dr. Nabil on artificial intelligence in process engineering. Dr. M. Nabil is currently working as assistant professor in chemical engineering department at IIT Tirupathi. He did his PhD in chemical engineering from IIT Madras, and his area of research is on optimization and control, machine learning for process systems, data reconciliation, state estimation, model predictive control, and data analytics. So he is having over 26 international publications, and also he has postdoctoral experience at Norway. So with this, I hand over the section to Dr. M. Nabil. You may continue, sir. Thank you so much.
Okay, I think now it's in full screen mode, right?
Yes, sir, it is.
Yeah, okay. Yeah, so thank you once again for the introduction. Today's talk is on artificial intelligence and process engineering. In this talk, I'll give a brief overview of what is artificial intelligence, and especially to process engineers like us, and how it has evolved, and provide a brief historical overview of AI in process engineering, and give some applications of AI which I have personally worked on, and give some pointers on how to approach an AI problem in process engineering. That's the brief outline of the talk. So let's start with what is artificial intelligence. That's a term coined at a math conference in Dartmouth in May 1956, and it was defined to be the study of how to make computers do things than what people can, than things that people who can do better. In other words, how can we outperform the performance of humans using machines? Okay. But even in our courses like computer-aided process engineering, we always focus or use computers only. Most of us will use only computers as only a computational machine, which means I give a set of equations and eventually use some tool to solve those set of equations to find out the solution. That's fine, and what it essentially means is it uses only the quantitative knowledge. Okay, when you give a process description, it lets you. Yeah, hello, sorry. Can you hear me now?
Yes, sir, we can hear you.
Okay. Yeah. So it gives you.
There are some disturbance. Is it fine for you to use some headphone or something? There is some noise coming from the back.
Okay, maybe I'll switch off the fan. How about now? It's better?
Yes, it is better.
Yeah, fine. Okay. So it's often perceived only as a computational tool. Okay. In other words, it uses only the quantitative knowledge, and there is no way it can accommodate the qualitative knowledge or the order of magnitude analysis that we perform on an engineering in general engineering. Therefore, avoiding such a knowledge is often detrimental in order to find or outperform the human actions. So the goal is to articulate, represent, and utilize all forms of available knowledge so that you can outperform human tasks. Okay. Fine. So if you look at way back in 1995, if you want to perform a large-scale numerical simulation, it is possible. It is also possible to store and retrieve the data, and also if we are about to do repetitive tasks, those can also be automated using computers. But what was not possible was how to respond. Okay, as humans, we respond to situations and we take decision making, right? That, and also to recognize when there are multiple things, how do we find similarities or distinctions, or how to respond to contrary messages. Those were not cannot be performed using computers. This is way back in 1995, but things have changed over a period of time. Therefore, the underlying philosophy of artificial intelligence is to make a mind rather than mimicking what to model a brain. To put it in simple words, okay. Why do I make that statement? Because modeling a brain is more like individual way of attacking a problem, like more like trying to represent the brain, okay. But when you make a mind, it means it has to have capabilities of responding to situations, the goals that we have set in the previous slide. Okay, so essentially we want these computer programs to be able to efficiently do symbolic processing and also utilize all forms of knowledge. Of course, as problem solving also, which we do, and the fourth aspect is the software design. Okay, we also need tools that can handle the symbolic computations as well as decision making at that time. So this is the underlying philosophy of artificial intelligence. So there are earlier attempts on using artificial intelligence and process engineering. It dates back to 1960s. The first application was in developing a process synthesis, automated process synthesis model, which is called the adaptive initial design synthesizer, and for the manufacture of ethyl acetate. The first system that was developed that employed AL, it used ends and means analysis. It had some amount of symbolic computations and linked the different data structures in chemical engineering. Okay, as you could see, the different elements of AI that we saw previously had been implemented to some extent. So this is, we call it as early attempts or phase 0 of AI in process engineering. The second phase of AI is the expert system setup. If you go to a process plant, okay, and try to observe what an operator does, he will try to have over a period of time, he would have gained how to operate the plant and have some set of rules. Okay, those rules are heuristic rules. That is the knowledge that he has acquired over a period of time. Okay, so this expert systems is nothing but the knowledge-based system or rule-based system which a process engineer already possesses. So it uses the, in a sense, it extracts the domain knowledge, okay, which the process engineer has and implements in the form of heuristics or rules, and try to use it for decision making. Okay. So that's why it's called expert systems, because the knowledge of the expert is being used as feeding as an input to the computer, and so that it can help in automated decision making. Okay, and several examples of the expert systems era goes back to 1977 Prospector, which is a computer-based consultant system for mineral exploration, like where to explore minerals and how to use it in the process industry so that you get the right quality of minerals and so on. And yet another applications on expert systems is on Con5, which is physical property decisions. Like in your thermodynamics, you would have performed VLE calculation or PVT relationships right? For as you see for different materials, how do you get that relationship? Okay, so basically it's a physical property decision. Okay, so depending on the material, you may need, given any material, you should have a data for all the gas molecules and PBT relationships, so that it can help you in automated decision making. And similarly for catalyst design and for catalyst design and similarly for catalyst design and also for developing even process models. And the second phase of AI in process engineering is on neural networks. Okay, unlike the expert systems era, where the process engineers' knowledge is being used in the decision making. Okay, in neural network era, we take the data. Okay, instead of the process knowledge that the process engineer has gained over a period of time, we use the data because data has been acquired and or stored in process historians for over a period of time. So you have humongous process data. Can we use that process data to help in identifying the patterns in the data and use it for decision making? Okay, essentially to use it for decision making. And this idea has been there since 1943. And the major philosophy of neural network is you can relate it to approximate nonlinear functions, highly nonlinear functions. That's the reason neural network was very popular. But the challenge there was, how do we train such a model? It was possible only with few layers of neurons, okay, few hidden layers in those times. So it was the training the model was tedious, it posed computational challenges. Okay, but still it has found some applications in discovery informatics framework for material design and automated reaction network generation. There are several papers on using neural networks for variety of applications. But until 2008 or so, it didn't gain popularity in terms of actual industrial practice. The reason was lack of computational power. We didn't have enough power, or the machines were not able to store a lot of data, as people, maybe your faculty who were using computers over the period of time could be able to relate that better, because we have seen how the machines have become better and better in just a decade time. Okay, and also the communication infrastructure, like the one that you realize today using Wi-Fi and the transfer of data, the use of smart sensors in transferring data even without a physical hardware connection. All those were posing challenges in those days. Okay, and also on lack of software as hardware and data themselves, and performing the AI or the consultant system or a recommendation system was too expensive, and it because of the lack of all other factors, the successful industrial implementation was a challenge. The current phase, which is the deep learning or the data science era, or you can also put it as machine learning phase, there are three important ideas that have evolved. One is an extension of neural network, which is deep or convolution neural network, which means there are several layers instead of few layers representing the nonlinear relationship. When you include more and more layers, it can represent the nonlinearity in the data much better. Okay, so deep learning was successful because of the computational power that we have today and the improvement in infrastructure, hardware infrastructure of all our sensors, actuators, and so on. Okay, and also in communicating between different systems, different process systems. Another important idea is on reinforcement learning, which is all about learning through interacting with the system. Okay, like we train a child, the child can learn itself, but we also give feedback to the child. Okay, when she or she is making an error in, say, I'm teaching an alphabet to my child. Okay, instead of B, she is writing it as B. Through interaction, I correct that. Okay, and achieve the goal of learning what we desire. The same we can do it for process applications also. So if I want to optimize the process by interacting with the process, how do we make better decision making is all about reinforcement learning. And thirdly, the statistical or probabilistic machine learning, which is to represent the process in an uncertain environment. So these are the technologies behind the recent AI success stories, not in chemical engineering or process engineering, but in other domains. AI has achieved significant milestones. One of them is the game of chess, when a machine defeated, which is the Deep Blue, defeated Gary Kasparov in 1997, which is one chess. What is it? It's basically several combinations. If you think of a game of chess, it's all several combinations. So how to win a game is among several possible combinations, right? The goal is to win the game, but it all depends on how you make different moves, right? So, and with the world best player of those time, Gary Kasparov. So this requires training a lot of models with the game of chess, and finally it was successful. And then there were on the game of Jeopardy, which is a question and answering based game, which Watson, the machine was Watson, which won the then champion Brad Ritter and Ken Jennings. And AlphaGo again is a AI tool that defeated Lee Sedol. He is the winner of 18 world titles, and this was possible in 2016. All this success were due to the technology on deep learning, reinforcement learning, and statistical machine learning. And all of these, in all these games, there are the key take home is there are different combinations. Essentially, it solves the optimization problems and train the models with different different set of games. And an essential take home is for process engineers like us, it all was possible because the system was deterministic. If you take a game of chess or the AlphaGo, the number of combinations, though there are infinitely many combinations, but still a pawn can move one step or two step or cross, right? Or the horse can take just an L shape, right? So in that sense, it's a deterministic problem. It's just that which choice you take is not clear, but still you can represent it as a deterministic problem. Whereas for a process engineers like us, the challenge is the data that we have, you take pressure data or the temperature data, it has uncertainty involved. They are not accurately known or known very precisely. There is some level of uncertainty. And also the model that we represent can be only approximated. So in such a uncertain setup, we have to take decision making. That's the challenge as process engineers we have. Okay, so the major thing is on the major development is on machine learning. So let me introduce what machine learning is. Machine learning, as you see different definitions posted here, it is often stated as the study of computer algorithms that improve our experience use of data. And the IBM definition is without any explicit programming, can form an AI system that can learn from data. But this is the third definition is from the textbook Murphy on probabilistic machine learning. It defines it as a set of methods. It's nothing but a set of methods that can automatically detect patterns in data and use those patterns to predict the future behavior and also help us in decision making. It could be predictive or it could be prescriptive. Okay, both are possible with machine learning, and that's what if you see any major paper in literature, it's all about using those methods to either for prediction or decision making. Okay, so let's briefly check on as process engineers, we have to, our wealth of information is in process data. So we have to understand the process data whenever we are going to apply a machine learning model or for decision making or for prediction. Okay, so one it could be homogeneous data like temperature, pressure, which are nothing but real numbers. Okay, it could be some real. I'd say temperature to be 215 degrees C. Okay, and flow rate to be say 1015 LPM or 15.1 LPM and so on. So these are real data. On the other hand, you also have categorical data. Means if you take a multi-phase system, it could be an annular flow or a slug flow or a stratified flow, or you take Reynolds the type of flow. Even in a single phase fluid like pipe flowing, could be laminar or turbulent. That's a categorical information, right? So, and which means we have different type of data, and it could be univariate and multivariate, and the data will be multivariate, but there are tools, the existing tools are on using how to do it for univariate statistics and multivariate statistics. So what essentially we need is a framework to deal with this high dimensional data. To give an example on the heterogeneity of data we have, if you take absorbance versus wavelength, and you see different images of a particle in a food processing industry. Okay, these are different type of data that represents. So it could be an image. It need not be just the real data, like the temperature that we have seen. It could be spectral data or it could be image data. So we have to deal with this heterogeneous data when we are trying to use the machine learning model. So there are different clusters. Probably if you are familiar, if you're not familiar, machine learning models could be classified as unsupervised learning or supervised learning and reinforcement learning. Unsupervised learning is all about discovering the patterns in the data. In simple words, it could be finding clusters or patterns. Supervised learning is, I have some y and x, trying to find the relationship between y and x. So that relationship, the y that I'm talking about, could be a real one, or it could be a categorical one, like the laminar versus turbulent flow, right? So when you have such a data, if I'm trying to map the y and x, then it is a regression or classification. And the third one is reinforcement learning, which will also employ some of the supervised or unsupervised learning method, but it is a direct goal-oriented learning through interacting with the system. Okay. Still some work on reinforcement learning or going on in my group also, but we have not progressed much on that. We are still working on reinforcement learning. But all the other two techniques I have extensively used during my postdoc and PhD. So here in the next part of the talk, I'm just going to present, maybe I'll leave with one application. Okay, the major work will be on data-driven modeling, monitoring and optimization and control. I don't know how much time do I have. Yeah. Hello. So in the interest of time, maybe I'll just present one of the application. Okay. second application. So in optimization and control, how do we use this machine learning in optimization and control? Okay. So here it's basically the mining industry, okay, where you can think of oil being present. It's basically an enhanced oil recovery technique. Okay, in places like Canada, you have what is known as oil sands, which is a mixture of bitumen, sand, and water in the surface. Okay, but what we require is to recover the bitumen from the oil sands, because it contains both sand, water, and bitumen in it. We want to extract the oil so that you can use it for you can refine it and then develop all petroleum and petrochemical products. Okay, so in this what you see is a steam assisted gravity drainage process that depicts how to produce oil. So essentially you have a well where you will inject the steam, and it will create a layer of oils, okay, softened oils. Because of the increase in temperature, it can just reduce liquefy the oil, which was initially in a semi-solid state. Okay, and there are holes in the pipeline that will let only the bitumen to seep through. Okay, and finally you will have a pump that will produce the oil from the second well. Okay, so this is the overall process of enhanced oil recovery in bitumen. And for this, our goal, as you could see from an energy viewpoint, okay, I want to use as minimal steam as possible. Okay, and therefore, because the way the steam, how do you get steam? You have to have a utility plant that generates enough amount of steam to produce oil. So if I have lesser amount of steam to one of the objective is have steam to oil ratio. Okay, that is what we call steam to oil ratio. Okay, and if the steam to oil ratio is low, okay, as low as possible, then you can say it is a measure to quantify economic performance. If it is low, which means the amount of steam required to get the oil was to get the required amount of oil is less, which means I need only limited amount of energy sources to produce steam. Okay, so with that as the objective, okay, what we use is over the period of time, as you could see, it's a learning process. So initially you give some historical data to get this steam to oil ratio, and you develop a model. Okay, it's a the model will be changing over the period of time. With the current data, with the existing data, you develop a model. That model, we call it as a surrogate model. Okay, between steam to oil ratio, and you then, once the model is there, you optimize, assume that as the model of the process, and you try to query the model. Okay, try to identify what is the next input I have to give so that I can span over the whole space. And with this, we query the black box model to obtain the next set of inputs. Then once you have the input, then you have new data as well. So you append the data and again reconstruct the model. So this process you go on. But with the goalless steam to oil ratio, as you could see, over the period of time, it was able to identify the inputs with minimal steam to oil ratio. Okay, then it suggests in optimizing, I don't have a physical model. Okay, unlike the first principle based model, we don't have that. With the data over the period of time, we have refined the model and tried to optimize the process. So then it tells, and it was also it tries to identify the best steam to oil ratio for the process. That's one example. The other is an extension of in control application. Basically, once you have the output, how do you achieve optimal control? Which means how do I use, despite uncertainties in the model? Because as you could see, it is a this modeling using first principle, it's really tedious. Usually people use some computational tools to mimic the reservoir setup. Okay, they will use a reservoir simulator. So under those scenarios, can we use the advanced model predictive control to achieve the goal is one of the work that we did, and we have found some application as well. So the take home pointer is in this is understanding the goal. If when you're trying to do a um, machine learning exercise for any of the application, understanding the goal is the first step. Okay, and also we have to have an idea of what different kind of process data we'll deal with. Okay, and more importantly, the mathematical foundations are very important if you want to troubleshoot. Yeah, you have enough tools like Python or MATLAB or different tools where you feed in X and it can fit the model to you. But whether the model that you have built is really meaningful, that only processing states can give you. And it also requires knowledge of the mathematics behind it. Then only you will be able to fix the issues. Say if it is giving some solution, whether the solution is meaningful, you will be able to understand only if you have a understanding of how the model is being built. And of course, the domain knowledge between within the domain and expertise, say from computer science, is also play a critical role in developing a successful ML application for process engineering. Yeah, thank you. This is part of the work I did during my postdoc with Professor Bia Huang at University of Alberta. So I'd like to acknowledge the group for the support. And thank you. I'll be happy to answer your questions.
Thank you, sir, for your wonderful discussion. So, participants, the session is open. If you have any queries, you may raise the questions.
So, are there any questions?
Sonu Sinha, you have raised the hand. Is there any questions from your end? Any other participants? Any?
Yeah.
No, sir. I think nobody is responding.
Oh, he has raised his hand. Yeah. Okay.
Yeah.
Maybe you can write an email.
Yeah, you can type the mail, and also you can contact sir if in case any questions are there, or if questions has to be clarified here, you can put it in the chat box also.
Right. Can I unmute him? I don't know. So, yeah, fine.
Okay, sir. I think no clarifications or questions.
Yeah. Okay. Thank you. Thank you very much.
Yeah. So thank you so much for your brief introduction about machine learning, which is one of the important topic that is being discussed in all the areas of chemical engineering as well as all the areas as well. So thank you so much for your time and effort, as well as sorry for the delay that has happened during the initial time because of participants couldn't join at the initial time. So to the participants, we have the next online section by Er.SHARJAH, Principal Process Engineer from Sharjah. So the session is from 2 to 2:30. So the link will be the same. I request all the participants to join using this link. Thank you so much.
Winner, winner.